Hello dear friends, welcome to a lecture on complex analysis. In this lecture we shall study theorems on limits. In our earlier lecture we have studied definition of limit, also we have solved some problems to show the limit using the definition of limit. You please refer these lectures, and now I have written here first theorem. Suppose that f of z is equal to u of x comma y plus I v of x comma y, that is this function f of z is expressed in terms of real function and imaginary part, real and imaginary part, where real part is function u and imaginary part is function v, where z is x plus I y is the complex variable, and z naught is x naught plus I y naught, w naught we have denoted by u naught plus I v naught. And then the theorem statement is limit of f of z as z tends to z naught is w naught if and only if limit of u is equal to u naught and limit of v is equal to v naught when x y tends to x naught y naught, or that is same as z tends to z naught. So, this is the theorem. It states necessary and sufficient condition for limit of a function, and that means its real part tends to the real part on the right side, that means function's limit, and imaginary part, that is v, tends to v naught, u tends to u naught and v tends to v naught. Or actually this statement is the limit of f of z, that means limit of this function u plus I v is equal to w naught means u naught plus I v naught, and therefore the theorem states that when limit of f of z is u naught plus I v naught, then u will approach towards u naught, or limit of u is u naught and limit of v is v naught. Because there are two conditions, we shall prove the theorem in two parts. That means statement 1 implies statement 2 and the converse part will be statement 2 implies statement 1. We shall first prove the converse part, that means statement second implies statement first. So, we will start the proof as in the first part we shall suppose statement second holds and we shall prove statement 1. We shall prove statement, the condition is if and only if. So, second implies first and also first statement implies second. We shall first prove statement 2 implies statement 1. And now suppose statement 2 holds. Suppose two holds. This statement is true. That is limit of u is u naught and limit of v is equal to v naught. And now we apply the definition of limit for this. So, therefore, for every positive number epsilon there exist and because these are two limits, we shall consider two positive numbers, delta 1 for first limit and delta 2 for second limit. There exist positive numbers delta 1 and delta 2 such that see the definition, application of definition for the first limit, such that the absolute difference of u and u naught is less than epsilon whenever the absolute difference of these two numbers x comma y minus x naught y naught, and we know how to take the absolute difference of these two. It is same as the distance between these 2 points, and that is whenever 0 is less than under root of x minus x naught whole square plus y minus y naught whole square and this is less than delta 1. Absolute difference of this is less than epsilon. This is the definition of limit of a function, and then is less than epsilon whenever this point x y lies delta neighborhood of this point, means distance between these two is less than delta 1. And the second is, now we shall suppose this as a third statement, and the second, for application of definition for this limit, that means the absolute difference of v, this v of x comma y is written in short as v, and v naught, v minus v naught is less than, and instead of epsilon we may consider this as epsilon by 2 here also, because why this is so, epsilon is arbitrary, we can replace every positive number epsilon. Epsilon is a positive number and it can be taken at our choice, it is arbitrary, whatever may be epsilon. So, epsilon or epsilon by 2 or epsilon by 10 or epsilon by 4 etc. we can select, and therefore, why we are considering this instead of epsilon, in the definition we have used epsilon, but here we are taking epsilon by 2, because next we want to add these two, and in the final expression we will have epsilon. Therefore, this quantity is taken as epsilon by 2, that can be taken at our choice whenever, and the condition, this condition remains same, but the neighborhood we can consider as delta 2, and that means whenever the absolute difference of this is less than delta 2. Here we have used delta 1, here we are using delta 2. X minus x naught square plus y minus y naught whole square, and this is less than delta 2, and we suppose this as 4. So, thus we have applied the definition of limit for this. Now, what we shall consider, both these inequalities will hold when delta 1 is delta 1 and delta 2, if we select delta as minimum of these two, or we choose delta is equal to minimum of delta 1 delta 2, then the inequality 3 and 4 will hold if we replace delta 1 and delta 2 by delta. Then inequality, second inequalities of 3 and 4. Holds if we replace delta 1 delta 2 by delta. So, this is because if we have this as delta 1 and delta 2, it is a neighborhood of this point, say x naught y naught is a point, suppose this is x naught y naught, and what is the delta 1 neighborhood will be this one suppose, and let us suppose delta 2 neighborhood is this one. See, this distance is delta 1 for example we are considering, and if this or vice versa may happen, whatever may be, this may be delta 2, this may be delta 1, and what we will have is, if we consider the minimum of this, here what is minimum, delta 1, and if the point x comma y lies in this neighborhood delta 1, then it also lies in the neighborhood of delta 2, and therefore we have, but if it lies here, it lies in the neighborhood delta 2 neighborhood, but it will not lie in delta 1 neighborhood, and therefore both the inequalities will be satisfied if the point is inside the minimum delta, and therefore that is why we have considered delta as minimum of delta 1 and delta 2. Now, we want to show this limit, that means this one, we have mod of f of z minus w naught, and this is what is f of z? F of z is u plus I into v, we are writing in short this as u and this as v. So, u plus I v, and w naught is u naught plus I v naught. and this is u minus u naught plus I into v minus v naught, and this is less than or equal to each value, that is mod of u minus u naught plus this is actually the triangle inequality, mod of z1 plus z2 is less than or equal to mod z1 plus mod z2, and what about mod of I? Mod of I is 1. So, therefore, we are not writing the absolute value of I, which is 1, and that is v minus v naught. So, this is the expression for absolute difference of fz and w naught. And now, what is this difference? That is x minus x naught under root of and see this one, root of x minus x naught square plus y minus y naught whole square. So, this is actually the difference of x plus I y minus x naught plus I y naught. You see absolute difference of this x minus x naught plus or this may be written as x minus x naught plus I y minus y naught, or which is same as mod of x plus I y minus x naught plus I y. And now we see if 3 and 4, from 3 and 4, what is the mod of u minus u naught? This is less than epsilon by 2, this is less than epsilon by 2, and what about mod of v minus v naught? That is less than epsilon by 2, and what about this? This is less than delta 1, this is less than delta 2, but we have chosen delta as minimum, and therefore this means this expression will be less than delta, and this will be the same condition for less than delta. So, from statement 3 and 4 we get, so I shall write here, this we will continue here. From 3 and 4 we get, now see, mod f z minus w naught is less than, this is less than or equal to this one, but what about u minus u naught? This is less than epsilon by 2, and what about v minus v naught? That is less than epsilon by 2. So, that is why we have taken instead of epsilon here as epsilon by 2, because we want to add to get the required result, we want to add these inequalities, and that is epsilon. Whenever now you see what about whenever this is less than delta, both will hold if delta is minimum of delta 1 and delta 2, and this means what? Mod of x plus I y, whenever mod of x plus I into y minus x naught plus I y naught, and this means z minus z naught, or this is 0 is less than, and this is less than delta, and thus, so this what this shows, mod of a, for every epsilon greater than 0 there exists delta greater than 0, such that mod of fz minus w naught is less than epsilon whenever this absolute difference of z and z naught, z is x plus I y and z naught is this one, is less than delta. This shows that limit of f of z is equal to w naught as z tends to z naught. So, this proves statement 1. This shows that limit z tends to z naught of f of z is equal to w naught, and therefore, the statement 1 is true. Hence, say a statement or thus statement 1 holds. So, assuming statement 2 holds, we have proved statement 1 holds. Now, the converse part, that is second part, we shall consider. See part 2. Now, suppose conversely suppose, or which is converse part, or actually we are proving this 1 implies 2, and that is actually the first part, but we now consider as we shall prove statement 1 implies statement 2. Suppose 1 holds. And one holds, statement 1 holds means what? This is true. Limit z tends to z naught, f of z is equal to w naught, and we apply the definition of limit for this one. So, therefore, for every positive number epsilon, there exists positive number, there exists a positive number delta, epsilon delta definition of limit. Such that this is from the application of the definition, such that mod of f of z minus w naught is less than epsilon, or this means what is f of z is u plus iv, and plus minus what is w naught? W naught is u naught plus iv naught, and this is less than epsilon. Whenever the absolute difference of z and z naught, and that is the difference of this x plus iy and x naught plus iy naught is less than delta. Now, we want to show the second statement, and for that purpose we shall have to show that the absolute difference of this u and u naught is less than epsilon, and v and v naught is less than epsilon when this is less than delta. Now, u mod of absolute difference of u minus u naught is less than or equal to absolute difference of u minus u naught plus I v minus v naught. So, this is obvious because this is real part of this number, and we know absolute value of real z is less than or equal to mod z, and that this is the result we are using. Real z is less than or equal to mod z, and this is real part of this. Real part, absolute value of real part is always less than or equal to the absolute value of the whole complex number. So, but what is this? This is same as this one, mod of u plus iv minus, which is same as mod of u plus iv minus u naught plus iv naught, and we will assume this as 3 and this as 4. And what about absolute value of v minus v naught is less than or equal to the same, u minus u naught plus I v minus v naught, and which is same as this one. and see this one. Also, what about the absolute difference of this? This is less than delta, and therefore from this 3 and 4 we will get or we can write like this as and this is also I shall write here also under root of x minus x naught whole square plus y minus y naught whole square, and this is same as the absolute difference of x minus x naught plus I into y minus y naught, and this is equal to mod of x plus iy minus x naught plus iy naught. You see this one. So, but what is this? This is we have written here. So, thus combining this using 3 and 4, what we will get? So, from statement 3 and 4, we get, now you see what about this mod of u minus u naught? This is mod of u minus u naught is less than or equal to this expression, and this expression is here which is less than epsilon. So, that means this quantity is less than epsilon means this quantity is less than epsilon. So, u minus u naught is less than epsilon, and what about this? This is also less than or equal to the same expression, and this is less than epsilon. So, here also we can write this is less than epsilon from 3, and thus v minus v naught is less than epsilon. Whenever see actually here we have to write 0 less than, strictly less than, because this is deleted neighborhood of the point, and whenever 0 is less than, this expression is same as this one. Whenever 0 is less than under root of x minus x naught whole square plus y minus y naught whole square is less than delta. And now what this shows? This shows that limit of u is equal to u naught by definition of limit, and limit of v is equal to v naught as x y tends to x naught y naught, because the absolute difference of this is represented here, and which is less than delta. And this proves, or this shows that limit x comma y tends to x naught y naught of u x y is u naught, and limit x y tends to x naught y naught of u naught v of the point v x y is v naught, and the statement 2 holds, and this proves the theorem. We have proved both the parts, second implies first, first implies second. Thus statement 2 holds, and this completes the proof, completes the proofs of the theorem. So, thus we have proved theorem 1 here, which is useful for further solving further problems. Using this theorem, we shall prove the second theorem in our next lecture. I hope you have understood this proof of the theorem first. Thank you for watching the lecture.